Hello YouTube, welcome back to part 3 of the Grass Shaders series. I'm excited to announce that I just finished my high school education. This means I'm gonna have the next 3 months to just constantly upload videos, work on my game, and upload development log videos. So it's gonna be great. There's gonna be a bunch of uploads, and this is the first one to finish or hopefully continue this series. And then once I'm done with this, I'm gonna be starting with my development logs again. Also, I'd like to thank everyone for helping me reach 4,000 subscribers. It's absolutely amazing. I never thought I'd be at this point, so thank you guys very much for that. So let's get right into continuing from where we left off last time, which was these bunch of white planes right here. Essentially, the goal of today's episode is to create the Fragment Shader. All the Fragment Shader does is goes through every pixel within each triangle and assigns a color to it. And the color can be based off of the light, off of textures, or just anything you want basically. And we're going to be texturing it and lighting it so everything actually looks like a proper grass plane and grass shader today. But in the next episode we are going to be making it move and like essentially setting it up so you can paint the grass as well. So in this episode, it is the creation of the Fragment Shader. Okay, so open up your grass pass.hlsl file and just notice this lit pass fragment method we have here. This is what is going to be creating the color. Right now we're returning 1111, which is basically a white color, and I already explained what these parameters are in the last episode, so if you want, go check that out before you watch this video. So the first thing that we're gonna do is we are gonna set up the normals of this vertex, or this like region of fragment shader basically. And the reason why we are setting up the normals again, even though we set up the normals here, is because now we need to flip the normal if we're looking at the normal from the wrong direction. So let's go ahead and set this up. We're just going to use a half-3 to store our normal world space, and we're going to say input.normal world space, and we are going to also normalize, so we can say normal world space equals normalize normal world space. So we just want to normalize it as well, and if VF is equal to false, that means we're looking at the back face. We want the normal world space to just flip. Okay, we just want it to like turn around, and the reason for this is when we do lighting, if you're looking at it from the direction where the light is not facing it, then there's no reason for that side of the grass to be lit. So if we don't do this, it will have uniform light throughout the grass and it will just not look right. Okay, next thing, we also need to just store our position world space, and I'm just gonna do this for sake of convenience because we have this long variable right now. So input.position world space and fog factor, and remember the W variable in this, so this is the actual fog factor given to us by Unity, and .xyz is the actual position of the vertex. Now that's all the setup we really need. Now we just need a half-3 color, and we're just going to set this to 0, 0, 0, and this is going to be our base color that we are going to work off of. Now I want to create the lighting now. So now that we have the color, we need to get the light, and this is actually really simple. Unity's provided us with this light object. We can just say light main light, and we now need to set it up. Now setting it up is really simple. For our case, there are a few other extensibility things that can be found in the GitHub, but we're gonna keep it really simple. We're just gonna say float for shadow coordinate, and we're going to say transform world to shadow chords position world space. So what is this doing? Well, nothing yet because we haven't created this function. Let's go ahead and do that. Let's say here we want a float 4 and we need to pass in a position world space. Now the thing with lights is making sure that the shadows scale across the different distances and look kind of similar. So we need to figure out essentially which cascade our vertex falls in, and once it falls in that cascade, we need to map the world position of the vertex to the coordinate space of that shadow cascade itself. Okay, so it might sound really complicated, but it's not. It's like one line. Let's calculate what cascade we're falling under here for this position world space. Okay, we can say cascade index, and we literally, all we have to say is compute cascade index position world space, and that does all the magic in the background. We never have to worry about it. And now we just need to multiply our given matrix. So we're given a matrix here, main light world to shadow, and that's a given matrix, and we're going to pass in the cascade index, and this will provide a matrix that allows us to transform our position world space into the shadow coordinate space. Okay, so we pulling out the shadow coordinates essentially, and we need the shadow coordinates to initialize our main light. I'm sorry if that wasn't the perfect explanation. I'm not like that familiar with these concepts to be able to explain it in a really simple way. Hopefully in future I can create a more detailed tutorial on this, but just know that all we're doing is we're passing in a world space, we're getting out shadow coordinates, telling our light essentially how to behave. Now we can just say main light is equal to, and we need to say get main light, and we pass in the shadow coordinate. So now that we have the main light, we can do all the magic from that. So first, before we do that, we need to get the how much the light affects the face that we're looking at right now. So let's say normal light, and we're going to use URP's official lighting function, the lighting Lambert, and I'm pretty sure it's just a simple combination of multiplying using the dot product to figure out the intensity of the light on the face. However, I'm not going to make any assumptions. It's just a simple function, lighting Lambert. You pass in main light dot color, main light dot direction, and we are going to pass in the normal world space, and we're going to multiply it by a value that I'm going to set now. I'm just going to call this light power, for example, and we're going to set to 0.05. Seems to be a value that works, and we're going to set to light power here. Now this is cool because it lights our objects, but I'm going to show you a issue with this technique. So we're going to set the color to equal to the tint, so this is the color that's given to us, plus the normal light. Now we need to actually output this, so we can say half for color, and let's just pass in 1 for the alpha value now. And if we go back, you can see that it's black. Well, why is this black? Well, look at the direction of the light. It's pointing in this direction, but it's black. Now if you go into this direction where the light is actually facing, you'll see that now light is actually affecting our object. Now we can change the color, and we can change the intensity, and everything's working as expected, but this just looks horrible, right? Because just because a light is facing away from the object doesn't mean that we should not be able to see the object, right? Just think about grass in real life. There's translucency. Now this is something that we have to incorporate for our grass to look even remotely good. Okay, so let's all we need to do is we need to copy this, and we just need to say inverse normal light. We're just going to pass in the negative of this, and we are going to create another thing called I'll just call it T power for translucency power, power, and we're going to pass in a lower value than light power, because remember, a bit of light will get scattered away when it goes through the grass, so we want only a little bit of that to remain with us. So we're going to bring both of these in now. Actually, I feel like I have already in one of my previous takes. Yes, I have these variables, so make sure you actually include light power, and let's include T power as well, our new variable. So now we have both of these variables within our shader. Don't be concerned if the compilation didn't work for you just then, because you have to make sure that you add the variables to your shader script. Now let's go down here, and let's add changes to T power. Now let's see how this looks. It looks horrible still. What? Oh, Yep, we're not adding it. Let's go add this as well. And there we go. Now we have some little like light reflecting through, and when we go onto the other side, it's much brighter. It kind of mimics how light really works, but not really. It's just really faked. So now that we have a bit of basic lighting, let's actually wait, actually this should be affected by our tint as well now. However, it seems not to be. Are we correctly bringing it in? No, we are not. We are using a float instead of a float 4 for the tint, which is the color. So let's go back in here, and now this should actually work as expected, and our light should still be affecting it very slightly. I think my light affectance values are a bit lower. So if I bump this up a little, yep, so our light is working, and our color and our tint is working as well. Now let's just check one more time, just make sure. Yep, okay, cool. Now we need to bring in the texture, and we need to make sure that we have transparency. So let's go ahead and do that. Let's go down here, and let's create our transparency. So all we need to do for transparency is we need to sample from the base map. So let's go and just call this A for alpha, and let's go base map dot sample, and we're going to say sampler base map input.uv.a. Now where is all of this coming from? Now if you go back here, we need to actually see that we have this little tag called main texture here on our base map. And essentially what this tells Unity is to set up these variables, because we're definitely going to use it. And what we're calling the sample, and we're using the sampler of the base map essentially to keep track of where we're sampling from, and then we're passing in the UV to get that actual color at that position that we're providing, and then we're getting the alpha value at that position. Now I would recommend learning more about this function because it's used essentially everywhere. So all we're doing is we're getting color at a point from a texture is all you need to know, and we're getting the alpha value. So how do we create transparency? Now it's not like actual transparency, it's faked transparency. All we're doing is we're saying, well, if the alpha is below a certain range, then just don't render it. Now if we don't render it, then you can see what's behind it, right? So that's the logic that's going to go into this. Now we need a little variable called alpha cutoff, so let's go ahead and add that as well. Call this alpha cutoff. Alpha cut off. This is a float. I'm gonna just pass in 0.1 or something like that, and I'm gonna copy this. We're gonna make sure that we actually bring it in, and we are going to use a handy little function called clip, and we're just gonna say a minus alpha cutoff. Now watch this as nothing happens because we haven't assigned a texture. Let's assign ourselves a texture. And we can see just barely. We can't see it yet because they don't have shadows, and it looks like, looks like we might have mapped our UVs wrong, or something really weird is going on, or my alpha cutoff is too high. There we go, just increase the alpha cutoff, and now immediately you can see that we have basic shapes appearing in the form of grass. Whoa, we have grass now. So we have all these textures here. The credit is linked below to the person who created these textures, and essentially if I cycle through them, you have varying grass types, and all it's doing is gathering the transparency from that and adding it to this. So now we have shapes for our grass, which is a step in the right direction. Now we only have a few more things we need to do before we have a functioning looking grass. Let's go back in, and the first thing I want to do is I want to tell you how we're going to add shadows to itself, right? So one thing that is very important for realistic looking grass is if you have like a grass, okay, let's pretend we have a piece of grass here on our plane. Okay, if it's all uniform, the uniform, like the color is uniform from top to bottom, it's gonna look really like bad, and essentially we can't tell apart the different grass elements. Now if you look here, you'll see that there is a little tint here from the dark color going up to the light color, and this not only helps it blend in with the ground, right? This is a dark greenish color, but it also allows us to have like the effect of self-shadowing, right? And that's very important. All we need to do for that is we know the UV coordinates at the top and the bottom, and we just need to lerp from the dark color to the light color in this fashion like this, and then we'll have self-shadowing, which is just a fake effect. Now we need to initialize this, so let's go back here and let's add another color. Let's call this darker. Yeah, my naming convention is really bad nowadays, but it's fine. We'll just copy this and we can change it later. Copy, and let's create a float 4 from our darker color, and then once we have that, we can begin the lerping process. So how do we do this? Well, it's actually really simple. All we need to do is we say color equals lerp color darker 1 minus input.uv.y. Whoa, okay. So essentially we're just lerping from our normal color to our darker color as the UV increases. Alright, so let's go back, and darker is undefined. Oh, let's just go darker here. And now we have the self-shadowing effect. Let's go in and check this out. Let's change this darker color to a darker green. And wow, there we go. Now we can actually see the different grass elements. Now I realized that our height and our base are just way too, just too much. So let me decrease our base, increase our height. And there we go. Now it looks like light is actually affecting it, but we don't have shadows yet. This is a proper grass shader at this point. Like, you could stop here and this looks pretty nice, but we need shadows. And also we haven't added fog yet, so we need to do that as well. So now that we have this with all the random direction and all that fun stuff, yeah, we just add shadows. So let's go in. Okay, to add shadows, it's essentially the same thing as this lerp function here, except it's using a few different other variables. So let's just create this here. We can say color lerp darker to the current color that we have, and we're going to clamp, and we're going to pass in main light dot shadow attenuation plus, and we're going to create another variable. We're going to call this shadow power. Shadow power float. We'll pass in I don't know, we'll check that's 0.35ish, and let's copy this again, make sure we add it to this, you know the drill. Oh, copy the wrong thing. Okay, now we have this thing called shadow power. Let's add it to this here, and we are gonna clamp this between 0 and 1. Okay, so what is going on here? Okay, essentially our shadow attenuation gives us a value that describes how much shadow there should be at a certain point. Now we can use this to just create like a just black color wherever the shadow attenuation is, but what we can do is we can lerp between the current color we have and the darker color of our self-shadowing color, right? And we can lerp between those two depending on how much shadow there is supposed to be at a certain point. And what this allows us to do is it allows us to blend the top color to the bottom color when there is shadow at that region. So if we go back, we have errors. Of course, I'm using the wrong variable name again. And we can see nothing has changed at all. Let's create a cube so we can actually test the effect of shadows. And already you can see that this is affecting our object. You can see the shadows on here. Now, why is why are we lerping between darker and color? Well, essentially, note how previously we had this, if you can notice the little blend here, we have this darker color here at the bottom and we're lerping to the normal color. But when there's a shadow, the entire region of that grass should be of this darker color, and that's all we're doing. We're just lerping the entire object, entire grass plane to the darker color. So if I change this darker color now, you'll notice that the actual shadow color changes, right? So if I put it to white, you can see really what's happening here. And we see the shadow color affects, the darker color, sorry, affects the shadow color as well. So this just gives us a cleaner looking blend between the bottom and the top, even when it is covered in shadow. Now we have clean looking grass that has shadows. What else do we need to do? Only one more thing, and that is the mixing of the current color with the fog, and that's literally 2 words. Let me go in and we just say here, say color equals the mix fog color, and we're gonna give in the fog factor, and our fog factor remember is our input dot position world space and fog factor dot w. And if we play this, nothing should happen. And let's go into our lighting, let's go into our fog, let's enable it, and let's just bump it up, and you can see now we have grass that is affected by fog. It's affected by light shadows, it has lighting, it has self-shadowing. Like, what more could you want, right? But we need movement, and we need to be able to paint it, or else it's pretty much useless. So that is what we are going to be doing in the next episode of this grass shader, and by the next episode we will have this result. You will be able to create this in the next episode, and since I'm free of any commitment now, I'm going to be releasing that next episode within this week. Thank you guys very much for watching, and remember, if you want all the source code, you can find it down below in the GitHub. And yeah, thanks for watching, thanks for helping us reach 4,000 subscribers, and I'll see you next time.